Okay, so let me quickly recapitulate a few things from our last lecture. In our last lecture, I hope you can see the screen. We have seen that if you have some system, non-relativistic mechanical system, which is defined as this classical action, which is the kinetic term, and you add additional potential term, then we have seen that this action, so therefore this describe a particle motion of a particle in presence of potential in flat space, Euclidean space. And we have seen that this action is dynamically equivalent to a motion of a particle in a curved background. Where Gij in no longer be the flat Euclidean metric, it will goes to the structure of Riemann curved space metric, which is defined in terms of following structure, which encode the information of the potential. So therefore, one can immediately observe that. So therefore, we just incorporate this mass term appropriately. So we can say that the particle moving in a flat space with the potential motion is dynamically equivalent to a free motion, but in curved space. So this was our observation. But now, today I am going to discuss the generalization of this concept. So today I am going to discuss a brief overview of linearized gravitational waves and their interaction with non-relativistic particles. But before going to detail of this technical purpose of the gravitational waves, so let me just introduce some brief idea of Einstein gravitation theory. Let us start from very basic standpoint. We know that the Newton gravitational theory, a Newtonian gravitation theory described through the Newton's equation of motion, which incorporate the trajectory of, which give rise to the trajectory of a neutral particle in presence of the gravitational interaction. And this phi is the gravitational potential, scalar potential, which defined through this equation. This is nothing but the standard Poisson equations, and where this rho is just a source of mass density, and which is nothing but the source time, and g is the gravitational constant. Which you can, those who are familiar with the electrostatic, one can recognize that this is nothing but the Poisson equation for the electrostatic case, where this charge distribution replaced by this mass distribution or mass density. So this is the standard theory of Newtonian gravity. But now ask following question. From our previous observation, we establish a potential motion is equivalent to a free motion in curved space. Now the question is, can we interpret this Newtonian gravitational theory? So Newtonian gravitational theory based on the potential motion. Can we reinterpret this Newtonian gravitational theory in a language of space-time geometry? Then I will move to the discussion of the Einstein theory of general relativity. So this is not a relativistic situation. This is non-relativistic classical mechanical situation. But as we have already explained that the geometric picture of classical mechanics provide us a nice interpretation to discuss the potential motion in terms of geometric motion. So now one can immediately observe this is the equation. This equation 25 is nothing but the equation of motion, which gives the trajectory. The solution gives the trajectory. Now one can interpret a curved trajectory in flat three-dimensional space. Due to presence of this potential, the trajectory no longer be the straight line. So this will be the curved trajectory over the flat space. Cartan first provide a interpretation where the curved trajectory can be interpreted also as a geodesic in four-dimensional curved spacetime. Please note that the today I am going to indicate in standard general theory of relativity start from the metric. As we have already discussed in our last class, metric is a fundamental notion to define the distance between 2 points in the Riemann space. But in order to establish the gravitation, the metric is not necessary. We need essential important object is connection. So therefore, the point is that in order to reinterpret this equation of motion as a geodesic equation of motion in some curved space-time, now we incorporate the time also the part of configuration space. So now one can rewrite this equation in terms of this structure. So one can introduce this four component object incorporating z component is time and other part is space component. And one can immediately rewrite this above equation, this Newton's law of motions in terms of the geodesic equation of motion. And one can immediately read off the non-trivial component of this Christoffel connection from this derivative of the potential. So one can immediately recognize only if we compare this equation 27 with 25, one can immediately recognize only the non-trivial component survive is gamma I00. And other components of Christoffel connection is zero, completely zero. So therefore, we can recast the Newton's equation for the gravitation in terms of the trajectory or geodesic motion of some given space-time. But the point is whether it is Riemann space-time. I am not claiming it is a Riemann space-time. It is just a space-time manifold. Incorporate some connection. Now, the moment you have the Christoffel connection, the standard one can define the standard definition of the Riemann curvature tensor, which gives the definition of the curvature, or it is a geometrical object which defines the geometry of the space-time. But still, we don't have any metric. We have only the connection which immediately read off from the classical equation of motion by reinterpreting as a geodesic of some space-time. So now, given this formula, one can immediately construct this following tensor. Now, for particular case, since we have only the surviving component of Christoffel connection is gamma I00, so one can immediately read of the non-trivial component of Riemann curvature tensor is just this part. So which is nothing but the second order derivative component of the scalar potential, because we immediately read of this Christoffel connection as a potential gradient with respect to the space derivative. So it is immediately recognized this R is Ri0J0 is just a second order derivative of the scalar potential. Now, if we consider the same index of I and J, which is already given from this definition of Ricci tensor, so one can immediately calculate the zeroth component of the Ricci tensor for the particular case, this particular situation, which is the situation for Newtonian gravitation. So one can immediately recognize the zeroth component of Ricci tensor is just gradient square of this phi. So therefore, one can immediately recognize the grad square phi is nothing but the curvature component which is associated with the Ricci tensor. So zeroth component of Ricci tensor can be read of this following expression. Now, also one can introduce the mass distribution. So we have already know that potential gradient satisfy this mass distribution equation. So this rho is just mass distribution. And given a mass distribution, one can multiply this the square of velocity of light, and which gives rise to the energy distribution or energy density. So this can be recognized as a T00 means the zeroth component of some second rank tensor. So which is known to be as the energy momentum tensor, which I will discuss later. But for the time being, we just consider this rho c square is just energy density. Now, the given Newton's law of motions, these potential expressions, this grad square phi is 4 pi g rho, can be recognized in terms of this Ricci tensor and the zeroth component of energy momentum tensor. So therefore, the point is that these give rise to the geometrical interpretation of Newtonian gravitational theory. So Newtonian gravitational theory can be viewed as a geometric part of the space-time, a given space-time, but still we don't know whether it is a Riemann space-time, because the Riemann space-time is only valid when the Christoffel connection can be derived from some metric, although which is called to satisfy the some condition is called metricity condition. But we still don't have this condition. We have this connection component, curvature component, Ricci tensor component, and we can recast the Newton's law of gravitation by this following structure. So what is the essential message one can obtain from this equation? These equations tell us if you have this energy density, this will be the source of space-time curvature component in terms of Ricci tensor. So therefore, this indicate that one can reinterpret Newton's law of gravitation itself as a geometry of space-time which can be emerged from some given energy density. So this is nothing but the geometrical interpretation of Newtonian gravity. So therefore, one can argue that whether the non-relativistic space-time still have some geometrical interpretation. And regarding this question, one can say the following comments. The geometrical, so therefore the following equation, so equation 27, from equation 27 to 33 is gives the geometrical formulation of Newtonian gravity. And this indicates that the non-relativistic space-time also have the geometrical interpretation, and this kind of geometrical interpretation in literature known as Newton-Cartan geometry. So the Cartan is first who realized that Newtonian gravity also can be formulated in a language of geometry. In our last lecture, we have seen that classical mechanics also can be realized in terms of geometry. So this concept can be extended at the level of Newtonian gravitation theory. So now the question is arise. So this gives the motivation. So here we aim to formulate the geometrical formulation of relativistic spacetime. So therefore, so far we just give some brief idea how one can reinterpret Newton's gravitational theory in terms of geometry. So this is just a motivation why we need geometrical formulation. So this gives some nice interpretation. If you have energy distribution, you will get some geometrical interpretation of space-time. Okay, we don't need to incorporate. So therefore, when you move to this picture, you just forget about the concept of potential. Now you are talking, now you reinterpret everything is just a curvature, effect of curvature. So now we wish to rewrite this expression in a general space-time coordinate transformation invariant fashion. So therefore, whether strongly speaking, it is not invariant. It's whether the question is whether we can rewrite these equations. One can immediately observe this equation only incorporate the zeroth component of some second rank object. So therefore, we have only the zeroth component of the Ricci tensor in adjusting by this energy moment, zeroth component of the energy momentum tensor. So therefore, we have only the energy component, energy density component. So therefore, can we rewrite this equation 33 in a covariant fashion so that one can recast this equation in a language? Covariance means it will transform in the same fashion under arbitrary coordinate transformation. So therefore, this is the point. So we want to develop the Newton's gravitational theory. We just first observed Newton's gravitational theory can be reformulated in terms of the geometry. Now we extend this formulation at the relativistic setting so that one can recast gravitational theory as a reference frame covariant way. So therefore, we just consider the space and time treating in an equal footing. So equal footing means we just incorporated the notion of metric at the level of space-time. So therefore, one can say that in order to obtain curvature, we don't need metric. In order to obtain, because the gravitational theory is based on the concept of curvature component. So therefore, in order to define curvature, initially, in principle, we don't need any metric. We need only the connection. But in general theory of relativity, we know the special theory of relativity indicate that we need to treat the space and time in an equal footing, and space and time, both of them treated as a coordinate, so that one can define the notion of event on the space-time, and one can define the distance between two events on the space-time. So therefore, we need to introduce metric in a standard in order to discuss the standard gravitational theory, which is known as Einstein gravitational theory. So this just consider the space and time in an equal footing, and time and space, both of them are part of the configuration space. And now the trajectory of the particle on the space-time just parameterized by some affine parameter defined, which satisfy this equation. So now, so therefore, one can label the particle trajectory in terms of this new evolution parameter tau. So using this reparametrization, this is one kind of reparametrization which already discussed in our earlier lecture. So if we write our equation of motion in terms of the reparametrization invariant way, so we observe that the equation looks like this following structure, which is basically purely covariant equations under arbitrary coordinate transformation. No. But to see the earlier equation, this equation, equation 27, is not the covariant equation because it is based on the time derivative. But now under reparametrization, we just re-express the equation in terms of this affine parameter, which is just evolution parameter, which this tau is not the part of coordinate. So now one can define that the tau, so at this level, tau is some arbitrary affine parameter. Now we need to specify the form of this affine parameter. Now we define the appropriate choice of this affine parameter in terms of the distance between 2 points in the space-time, which incorporated the notion of metric. And this d tau now is, which satisfy this equation, is known to be as the proper time, which is a scalar, which is basically a scalar object. And this d tau also can be rewrite using this following structure, because the ds is basically nothing but a line element between 2 points in the space-time. So now, the moment you define this d tau using this metric, so one can re-derive this geodesic equation from the action principle. One can postulate this is the action of a particle moving in the curved space-time, which incorporate this metric, and this space-time is considered as a Riemann manifold and non-Riemann space-time, and the space-time metric also provide the definition of this Christoffel connection. So the moment the Christoffel connection satisfies this expression, then we call this space-time is Riemann space, or this connection is called Riemann connection or Christoffel. Now, if we study the variation of this action, one can also achieve from this expression as a geodesic of the particle or point particle moving in this curved space-time. So this is the free particle action in curved space-time. So now let us point out important concept of Einstein theory, general theory of relativity, which is called Einstein equivalence principle. So this principle tells us the effect of any gravitational field can be absorbed by introducing the concept of local inertial field. So locally, one can absorb the concept of gravity. So this indicates if you consider a single particle and it's just considered a free falling along the geodesic, so it cannot experience the effect of gravity. So does not feel the gravity. due to presence of the gravitational wave. So this is situation considered at the very locally for the free falling particle. So in order to see the effect of gravitations in our concept, in our context, it should be the gravitational waves, which I will discuss later. But to see the effect of gravitation, so any observational effect of gravitation can only be observed if we consider the relative motion of two free falling particles. So if you consider a single particle and if you consider the local frame, so therefore you cannot realize the effect of gravity, just like a free motion of the lift. So any free falling observer cannot experience the gravity. This is just a fact of the Einstein equivalence principle. So in order to see the effect of gravitation, we need to consider the motion of, instead of single particle motion, we need to consider the relative motion of at least two particles, two massive particles. And one can immediately observe the geodesic of a single particle satisfy this equation, and the relative motion of two particles which satisfy the individual geodesic, and they can be rewrite in this following structure. So this structure is known to be as the geodesic deviation. And this geodesic deviation you observe that the right hand side of this geodesic deviation involves the Riemann curvature tensor. So now the geodesic equation involve only the Christoffel connection. And you know that this Christoffel connection is a good object. It does not transform in the appropriate way under the coordinate transformation. So, but this Riemann curvature tensor is no longer be zero in local inertial frame also. So therefore, this geodesic deviation of equation always involved or incorporate the effect of gravitation. So therefore, this is the indication that we need to consider the relative motion if you want to see the observational effect of gravity. So now, as we have already promised that we need to formulate the Einstein theory of relativity as a geometrical point of view of space-time. So therefore, we need to rewrite the Newtonian gravitational theory, which is discussed in terms of R00 and T00 in a covariant. So let us consider, or let us allow to write the all component of Ricci tensor, which proportional to, or which is of the order of the second rank object, which is known as T mu. For the Newtonian's case, in Newtonian case, we have observed that only the zeroth component of these equations survive. But in the general relativity, this is the motivation. But now we are consider the most general situation. So therefore, we just allow to consider this R mu nu, all component of R mu nu and all component of T mu nu, which is basically the second rank object, the Ricci's tensor and the energy momentum tensor of the matter. But please remember the point that we already experienced from the Newtonian gravitational theory, that energy density is the source of curvature. So this is the basic, or this is the backbone of Einstein theory of relativity, general theory of relativity. So we need matter distribution to incorporate the effect of curvature or gravitation. So the existence of matter and the effect of curvature is just some interrelated to each other. So now we just consider the Riemann Ricci tensor, all components, and which is proportional to this T mu. So now, in a most general case, it can be possible write down not only the T mu nu, apart from T mu nu, we also allow to add additional term, which is basically the effect of the trace of this T mu. It is a second rank object. You know that this is you can visualize this is a 4x4 matrix in a 3+1 dimension or 4-dimensional Minkowski spacetime. Minkowski spacetime. So therefore, it's a 4x4 matrix. So therefore, the matrix has all diagonal of diagonal component. Also, it has some sum of all diagonal component, which is trace. So therefore, we write down the trace part of this T mu nu along with the energy momentum part. So this is the most general structure of Ricci tensor, which is balanced by the effect of energy momentum component tensor component. So now, in order to figure out where at this point A and B are arbitrary constant, because our intention is to write down the generalized new gravitational theory in a relativistic spacetime. Because we have already seen the gravitational theory can be experienced from the concept of curvature, zeroth component of the curvature tensor. But now we are allowed to write down the gravitational theory in a covariant way. So in terms of all components. So in terms of all components, when you try to understand what is the exact form of this R mu nu, with depending on this T mu nu and the trace, we need to figure out this arbitrary constant A and B. So therefore, we need to identify an appropriate expression for A and B. So in order to identify this arbitrary constant A and B, we have some condition or initial condition. So the point is, let us consider the non-relativistic approximation or non-relativistic situation. This trace part of the energy momentum tensor can be written in this following component form. One can split into component form. So these are the zeroth component, and we know that if you down the one index from contra to co, so they pick up a minus sign. So this is the expression for the trace part of the energy momentum tensor. Now, if you use the weak gravitation and for a slowly moving matter, if we consider the matter is very slowly moving, then this this metric, and if you consider the gravitation effect of gravitation is very, very weak, this metric can be approximate in this following fashion. So therefore, this is just a part of the usual flat space-time, Minkowski flat space-time. And this is the part is just a deviation from flat space-time. It is just a very weak effect. So point is that we need to calculate A and B. So therefore, we just consider a simple situation to extract the form of A and B. Because the moment you can find A and B, since A and B is a constant, so if you impose any condition to find out A and B, and this form of A and B remain same for arbitrary condition. So now, so using this linear approximation, this is called the linearization of the metric, one can just consider the zeroth component of the equation R mu b. So the zeroth component is just R00. And one can immediately observe this right-hand side can be rewrite in this following fashion, because this second term provides us T00. Also the first term provides the T00. So one can club together, and you observe that the spatial sector gives rise to this second term with minus BTII. Okay. So now, if we consider Newtonian limit or Newtonian approximation, Newtonian limit means the particle moving very, very slowly, or matter distribution moving very, very slowly. So this slowly moving matter distribution, one can realize that this spatial part of the trace is zero, which provide the pressure component. So if you consider the pressure for the non-relativistic approximation, just zero for this low moving or slow moving particle. So then one can observe, if you ignore this part due to the low velocity approximation, one can observe this R00 is just A plus B T00. Now it will remember us the expression of Newtonian gravity in terms of the curvature. Any questions? Can you hear me? Hello everyone, can you hear me properly?
Yes, we can hear you.
Okay, fine. So now this expression is just a gravitational theory of Newtonian gravitational theory in terms of the curvature and energy density. So now if we compare the general relativistic situation at low velocity limit or non-relativistic limit with the Newtonian gravitational theory, one can immediately read off the sum of A and B is just minus 4 pi g, just considering C is 1. For the simple situation, we just consider velocity of light is said to be unity. So this is the condition imposed, one can observe that A and B are not independent. They satisfy this condition. Now, on the other side, one can observe that one can define also the new second rank tensor, which is called the Einstein tensor, and which involves, sorry, this should be mu. It should be mu. And this is just R mu nu minus half G mu nu R. This is the definition of G mu nu. And since we know the R mu nu satisfy this equation, so if you substitute the form of R mu nu, and one can immediately compute R in terms of the trace of the energy momentum tensor. This is very easy to compute because if you just consider the trace from both sides, this R mu nu, if the definition of trace is just given by this following expression. Since we have R mu nu is just A T mu nu plus B G mu nu, some T alpha. Alpha is a trace part. So if you just multiplying both sides by G mu nu, and G mu nu, you will get this is called the Ricci scalar. And this again is just give rise to T mu mu. And you can immediately observe this part is just G mu is contracted to get some number, and you will arrive this following structure, which is already written in this expression. So therefore, G mu nu, when written in terms of R mu nu and R mu nu can be rewrite in terms of energy momentum tensor and that its trace. So one can rewrite everything in terms of energy momentum tensor and the trace component. So now, this G mu nu satisfy some important property. So this property is called this known to be as the conservation of G mu nu or Einstein tensor. And this conservation of G mu nu is based on the conservation of energy momentum tensor. So this conservation principle of this G mu nu and incorporating the conservation of this energy momentum tensor, one can also obtain another equation which is basically just indicate that B is just minus A by 2. So if we just substitute this B expression of B in equation, this above equation, so one can immediately read off the form of A is just fixed by minus 8 pi g. And the moment you fix the form of A minus 8 pi g, one can immediately compute the B. So now we need this arbitrary constant. So now this arbitrary constant fixed by two consistency condition. One is the non-relativistic limit, other is the conservation of Einstein tensor. So these two condition, using these two conditions, one can fix this arbitrary constant A and B. And the moment you fix this arbitrary constant, so therefore the point is that why we need the non-relativistic? Because we want to get back Newtonian gravitational theory. Newtonian gravitational theory is just R00 and T00. So therefore, our generalized theory should be reproduced the Newtonian gravitational theory at some particular limit. So therefore, this limiting condition should be somehow incorporated in our arbitrary constant A and B. So that is why we just consider the limiting situation to find out this relationship between A and B arbitrary constant. And then the conservation principle fix this one other constant. So one can immediately extract the A and B is just satisfy this equation. And one can conclude that the Newton's equation of gravity or Newton's theory of gravity in a general relativistic setting can be reinterpreted through this equation. And this equation is most fundamental equation, and this equation known as Einstein equation. So therefore, this equation one can immediately check for non-relativistic limit can reproduce old Newton's gravitational theory. So therefore, in our theory, since we already incorporated the information of non-relativistic limit, so therefore, if we take the non-relativistic limit, the final expression of Einstein equation, it can reproduce this equation. So therefore, again, we get back the Newton's theory of gravitation in a language of energy density and curvature, zeroth component of the curvature tensor or Ricci tensor, which is defined in this way. So therefore, in the most general setting, we can build up the theory of gravitation in a language of space-time geometry. And the space-time geometry is not arbitrary. The space-time geometry fixed by the notion of distribution of matter. Now, the point is the matter distribution has several components. In a non-relativistic limit, we claim the spatial components and only the zeroth components are why because the low velocity, because the other spatial component based on the velocity of the particle. And if you consider the velocity of the particle is very slow compared to the velocity of light, then energy momentum tensor survive only the zeroth component and all component can be ignorable with respect to the zeroth component. So, but in case of a moving particle or moving matter distribution where the velocity is not very small compared to the light. So if we consider the relativistic regime, then we can't ignore the other spatial component of the energy momentum tensor. And this all components of energy momentum tensor is relevant to contribute the notion of geometry. So therefore, the geometry can be fixed by the structure of energy momentum tensor. Now the question is arise that how one can obtain the energy momentum tensor from the geometry, or how one can obtain the expression or exact form of energy momentum tensor. So this suggests us, so this equation tell us that somehow energy momentum tensor, so this is the existence of matter. The right hand side of this equation is just a concept of matter or energy or mass. So the concept of energy or concept of mass is just interact or somehow intimately connected with the geometry. So therefore now the space-time cannot be fixed. Space-time also show up some dynamical nature because the right hand side is a dynamical object. So right left hand side should be dynamical. So in Einstein theory of gravitation, space-time also behaves as a dynamical nature. So space-time and matter both of play the vital role in dynamics. So now the question is how one can obtain this expression of T mu or this geometry component of the particle. So in order to obtain this expression, one can observe that it is a very standard definition. Suppose you have the action of a particle in curved space. So we already mentioned that the action of a particle in curved space is just integration over G mu nu dx mu tau dx mu tau. So this is the structure of the action of a particle in curved space. Now the energy momentum tensor defined as this is the definition of energy momentum tensor. Just define covariant fashion. Sorry, let me say it is just I. So if you study the variation of the action with respect to the metric, one can obtain the energy momentum tensor. So therefore, from this expression, one can observe that is T mu nu, it just looks like M naught d tau. After some short calculation, you can immediately observe this is just dx mu d tau dx mu d tau just 4 x minus x tau. So So there are two coordinates. One is x, other is x tau. X is arbitrary space-time coordinate, and x tau is just a trajectory which parameterized by this affine parameter or proper time parameterization d tau. So if this tau is not arbitrary affine parameter. We already said that ds d tau is just c. So therefore, we just consider only the proper time parameterization. So then we get the expression of t mu nu is looks like the following structure. And one can also observe this from this expression. From this expression suggests that the variation of action can be cast as the variation with respect to g mu. So therefore, this indicates that the matter distribution interact with the geometrical component, which is a metric, variation of the metric, which remind us the situation for the interaction of charged particle in magnetic field. Those who are familiar with the classical electrodynamics, you immediately recognize that the interaction between the charged particle with, or not charged particle, any matter distribution, when the charge distribution interact with the background electromagnetic field, the situation is just A mu and J mu. So therefore, in case of the gravitational theory, it is just minus root g d for x. It's just a t mu nu variation of g mu. So now one can immediately observe that this here the point is the, let me say this way, g mu nu the play the role of a mu, something like that. It's just very analogical part. So therefore, one can recognize the current for current is just analogous to this energy momentum tensor, and this A mu analogous to this G variation of this G mu. So therefore, this suggests that the energy momentum tensor always interact with the metric variation of the metric. So, so from this point, one can compute the structure of energy momentum tensor. So energy momentum tensor, when the moment energy momentum tensor is given, now you can compute the geometry of space-time by solving this equation. But it's a very complicated solution. Now, this is the point. The how one can solve this equation? There are many ways to calculate this equation. The most popular way is a vacuum solution. So now, point is that we need to now what we can introduce. Now we are in a good position to introduce the concept of gravitational waves. So for the time being, we consider the T mu nu. Suppose T mu nu is matter distribution is zero. So therefore, is the vacuum, there are no matter distribution where the gravitational theory is just used. So now this situation can be incorporated through the notion of Einstein-Hilbert action. And this Einstein-Hilbert action tell us that if we study the variational or variation principle of this action, one can achieve the Einstein equation with the zero energy momentum tensor, which is the vacuum solution, which gives the vacuum solution of the metric. Now, consider the linearized version of the gravitation theory, as we have already mentioned, that the metric tensor can be approximate to the flat Minkowski metric and just a small perturbation. Small, very, very small perturbation, which is just a weak effect of the gravity over and above the flat space. If you view in this way, then all component, geometrical component, the Christoffel connection and Riemann tensor loop can be rewrite in this following structure. And using this following approximation, one can also approximate the Einstein-Hilbert action up at the level of quadratic, because we want to observe the equation of motion at the linear level, linear edge. So therefore, we need to consider the action is a quadratic form. So therefore, this is the approximate form of the Einstein-Hilbert action up to order of h square. H is the, again, h is the trace of this h mu nu, which is a 4x4 matrix initially. Now, the point is that this action is just a scalar under space-time, flat space-time transformation, which is known as the Poincare transformation. And also this action enjoys the, apart from the space-time transformation, this action also enjoys some internal symmetry, which is known as a gauge symmetry, which manifested by the transformation of H in this following fashion, where chi is just arbitrary parameter, arbitrary variable with of the space time. So now one can obtain the Einstein equation from this Einstein-Hilbert action for the vacuum. So we observe this following structure. And now this structure is so complicated. Now the point is that our intention is to find out the solution of this Einstein-Hilbert action. The solution gives the, so as we have already mentioned that if we have the energy momentum tensor, then you get some solution of, one can expect some solution of Einstein equation give the metric. So in absence of any energy or matter distribution, also we can obtain some solution of the metric. So this is the point. What is the solution of this equation? The solution of this equation can obtain only if we provide some other condition, because as itself, this equation, we observe this equation cannot be solved because this is the non-invertible differential equation. So therefore, we need some additional condition, and this additional condition is known as a gauge fixing condition. So gauge fixing condition means, it is quite well known that if you have a gauge symmetry in an action, it is just a very important concept. If you have any gauge symmetry in a dynamical model, in order to obtain the solution of the dynamical variable through the variational principle, we need to spoil the gauge symmetry. So therefore, in order to spoil the gauge symmetry, we need to gauge fix. The gauge fix condition in the standard gauge fixing condition is known as transverse traceless gauge fixing condition. And this transverse traceless gauge fixing condition defined through this following expression, where the first part is just provide. So H0 mu means indicate you have 4 equation, which is 0. The second part, which is basically the derivative of h with respect to space component, is 0. So this gives the 3 equation, because I is run from 1 to 3 space index. So therefore, we have 4 equation, 3 equations, so 7 constraint. And one can observe that this h mu nu, it is basically trace part of the metric. So trace is 0. So if you consider again the trace is 0, so therefore we have 8 constraint over and above this variable. Now the point is that with this constant, so as we have mentioned that we have gauge fixing condition is necessary to solve the Einstein equation in the linearized level, so that we have h mu 0 is 0, it's the one condition. So from this we have the 4 condition. Del I hij 0. From this we obtain 3 condition, and the trace part h mu 0, we obtain the single equation, 1 condition. So therefore, total 8 conditions. Now it is well known that the metric is just a symmetric tensor because it defines the distance between 2 points. So therefore, this metric is just a symmetric rank 2 tensor. So the symmetric rank 2 tensor, the moment you linearize G mu nu as eta mu nu plus H mu nu, which is a function of x, it's initially it is a 4 cross 4 matrix for 3 plus 1 dimension. So therefore, any 4 cross 4 matrix is provide 16 components. Now, so now question is how many number of independent components? So therefore, the number of independent components can be observed that we have 4 diagonal terms. So if you remove the 4 diagonal terms from 16 components, so you have 12 components. One is upper half triangular as a lower triangular. So here is 6 and here is 6. But these 6 components, due to symmetry, this H mu nu is H nu mu. So therefore, the upper triangular components is just exactly equal to the lower triangular component. So how many number of independent components? The diagonal, any one of the lower and upper triangular. So therefore, we have 10 independent components. But we have already mentioned that we have 8 conditions over and above the 10 independent components. So the 10 initial independent component, but using this gauge condition, it will reduce to 2 independent components. So therefore, the gravitational theory at a linearized level, incorporating the transverse traceless gauge condition, involve only 2 independent degrees of freedom. And these independent degrees of freedom fix the polarization of gravitational theory. So that is why one can argue that due to 2 independent components indicate that the gravitational theory when quantized, we expect that the gravitational quanta of gravitational theory will be the spin 2 particle. So which is basically the polarization state. So 2 polarization state. So these 2 polarization state, by the way, now this is the gravitational equation. So now using this condition, this complicated equation, nonlinear equation boils down to the simple looking form. And this simple looking form, since we only consider the non-trivial space component, all space time and time component are 0. So therefore, we are looking at the diagonal or any block of the 4 cross 4 matrix, which is a spatial block. Now, since it is a standard wave equation, one can propose the plane wave solution, and the plane wave solution indicate that the propagation of the wave, now we interpreted the gravitational theory as a wave-like nature. So therefore, the gravitational, this is the concept of gravitational wave. When you linearize and incorporated this condition, the perturbation of the gravitational over and above the flat background behaves as just a ripple of space-time over and above the flat space. So incorporating this concept, one can observe that this epsilon is just a polarization tensor, which is only 2 independent mode, and which is called the epsilon plus and other is epsilon cross. This should be cross. And since the Hij is a traceless, so therefore we must consider the diagonal term equal and opposite. So therefore we have 2 independent mode. One is the cross and another is a plus polarization. Now let us come back again the geodesic deviation, because we want to see the observational effect of the gravitational waves on the matter of some test particle. So now if we consider again the geodesic deviation equation, this geodesic deviation equation since involve this Riemann tensor, curvature tensor, and if you consider this geodesic deviation define the relative motion of 2 particles moving along their trajectory. Now, if we consider the non-relativistic limit, if we consider the test particle is moving very slowly, then this above equation boils down to this following structure. Now, one can recognize that these equations again look like they're Newton's equation of motion, which left hand side is just acceleration, and right hand side define the force term. And at the TT gauge or TS transverse testless gauge condition, one can read off this curvature component is just a second order time derivative of the metric component. So if we consider, so there are two conditions already incorporated. One is just a very, very slowly moving test particle, and the dimension of test particle are very small compared to the wavelength of the gravitational source. So therefore, when you consider long wavelength approximation, then the plane wave solution, this expression e to the power k dot x involve the time part and space part. The space part is completely die out. So using this approximation, we arrive at the geodesic equation, geodesic deviation equation looks like a very simple form, which is basically looks like a Newton's law equation of motion. So here we have made use the following approximation. So we consider the gravitational wave propagate along z direction. So therefore only x and y component are survived, and long wavelength approximation we can ignore, the spatial plane wave part is just one. So observation is that at TT gauge, the long wavelength approximation, the whole analysis effectively described by the Newtonian mechanics. And the component of gravitational waves in TT gauge just provide us the tidal effect. So therefore, one can observe that this effect of gravity, the effect of gravitational wave behaves as a forcing term, and which fix the acceleration. Now, if we consider a mechanical model instead of free particle to test particle, if we consider a mechanical model incorporating some mechanical potential, then the equation of motion, since we consider the free particle, relative motion of free particle, where the left hand side is acceleration, right hand side is the force term. Now, if you add some mechanical force, so the first term is the geometrical force, but if you add some mechanical force, this will which can be derived from some additional external potential, then we get some effective equation of motion, where the right hand side involve the force due to the gravitational waves and the force due to the external potential. Now ask the question, since we have effective non-relativistic equation of motion, can we rederive this equation of motion from some Lagrangian? Because in our first lecture, we have seen that if you have equation of motion, one can construct the Lagrangian by using the reverse engineering method. So therefore, we are fortunate that one can construct the Lagrangian for a point particle, which can describe the relative motion of the system of two particles in terms of the equation of motion, wherein this equation of motion can be derived the principle of variation of this Lagrangian, which incorporated the potential term and the gravitational interaction. So the moment you have the Lagrangian in the classical mechanics, one can also construct the Hamiltonian. The Hamiltonian is just involve this term. So therefore, this last two equation or just the last equation, we have the Hamiltonian of a system of particles which describe the relative motion of two particles in presence of gravitational waves and external potential. And we can consider this is the just as a detector of gravitational waves detection. So therefore, we can consider this model to extract some significant feature of linear gravitational wave detected in the LIGO, and whether we can ask the question whether this model also enable to provide or to show up the some quantum effect of gravitational wave if we promoted entire model at the level of quantum mechanics. So therefore, at this level, we can discuss the interaction between a point particle with the background gravitational wave through the following Hamiltonian. Okay. So I think we can stop here for today's discussion. Sorry, can you hear me?
Sorry, Partha.
Okay.
I was on mute.
Oh, okay.
So no, I can hear you. Yeah.
I see. Okay. So I am done. I mean, I just complete
Are
this
there
lecture.
I didn't see many questions in there was only a comment from Joseph Kiroi in the chat, but maybe you
I see.
already resolved it on the way. Are there any questions for Partha? We are not so many, so you're most and welcome just to unmute yourself and ask. This is set up as a meeting. It's not a webinar. You're welcome to. Everything is clear. Okay, Partha, then it seems that nobody has questions for you at this stage. As
Okay.
um, a- as we did last week, if you share the slides with me, I will forward it to our webmaster and upload them on the website next to the announcement of your mini school. And the video of today's lecture should be by I assume by tomorrow sometime in our YouTube channel. Yeah. So,
Okay.
Pat,
Okay.
thank you very much for another exciting lecture. Yeah,
Okay.
and hopefully next time the participants will give you a little bit more feedback.
Okay.
Yeah.
Thank you.
Otherwise, we do a test. Yeah.
Okay. Okay. Thank you.
Okay. Wonderful. Thank you so much, everyone. Thank you for joining us again. And please join us again next week for lecture number 3. Yeah. Thank
Yes.
you. Thank you very much. Thank you.
Okay.
Bye. Bye bye. All the
Bye bye.
best. Thank
Thank
you.
you. Thank you.